Okay, so first, starting from next lecture, we'll have a password for Zoom, which is 36 Turing, all in lowercase. I'll also send an announcement on EdStem, so keep that in mind. And so last class, we talked about, what this course is about, how is the grading, assignments, exams, all that stuff going to work. And we also started by talking about how to represent objects, right? We wanted to talk about what computing is, so we had to decide what to compute on. And we're not going to build a different model for processing images versus processing text versus processing graphs or processing videos, none of that. We're just going to have one uniform representation, which seems like a pretty, strong abstraction, right? We're going to view the entire world as binary, but that's for good reason. And because that's exactly what happens on your computers. At some level, that's happening. So let's open up this black box and see how it's done. Okay, and we're going to talk about that today. And finally, we'll introduce our first reasonable and powerful model of what computers should be. Okay, any questions about the last lecture? We'll quickly, maybe go over some of those things again today. All right. So what did we end up with in last lecture? The idea that we had was if we had representations of integers. Okay, so someone gave us an encoding function of integers as binary strings. We can then, from this, we use this representation to build a representation for pairs of integers, right? And pairs of integers was just rational numbers. So we built a representation for them by using the one that we had for integers. So today what we're going to do is kind of abstract this much further and do it in general. Given a way to represent certain class of objects, we are going to be able to represent tuples, lists of those objects, and then by composing it, everything. All right. So the core principle behind all of this, which gets used in pretty much any modern programming language, is the simple idea of what is called prefix-free encoding. And it's very old, but still just as useful. Okay. So what is prefix-free encoding? It's a special kind of encoding. Encoding, as so far we said, requires only one property, which is that the mapping be 1-to-1. There are no two objects which kind of map to the same binary string. But today we're going to require that encoding satisfy one additional property. What is that property? So suppose I have an encoding function from a collection of objects to binary strings, right? We will say this encoding function is prefix-free if the following holds. If I take any two objects, any two distinct objects in my space, the encoding of X is not a prefix of E of Y. Okay. So not only we just said for encodings, two distinct objects should map to two distinct strings, but now we are requiring that each string not be a prefix of the other. Okay. So, if I had X, I do the encoding, I get some binary string. It says 0, 1, 0, 1, so on. Maybe if I do Y, I get something else, which maybe is a little bit longer. 0, 1, 1, 0, 1, and so on. But the encoding of X cannot match what's at the beginning of Y. Okay? Does the definition make sense? And remember what I said in the last lecture, definitions are more important than the statements of theorems, more important than the proofs. So if the definition is not clear, please stop me. Okay? So let's look at some, examples, right? So we saw the representation of natural numbers to binary using binary representation. That was a valid encoding. It mapped natural numbers to binary strings. That's how, we denote binary natural numbers on the computers. Is this prefix free? Yes or no? No, right? So as an example, if I take, let's say, n to binary of 1, that gives me the string 1, right? And if I go to n to binary of 3, I get 1, 1, right? So I have two distinct numbers where the encoding of the first number is a prefix of the encoding of the second number. Okay, and it happens many times, right? If I do n2 binary of, let's say, 2, that is 1, 0. What is n2 binary of 5? 1, 0, 1. Okay. Once again, we have this violation of prefix freeness. All right. But on the, yeah, go ahead.
Does that mean that we can't, in prefix free encoding, we can't have encodings that are just maybe one or two characters, because no matter what, they'll always be a prefix?
Maybe, maybe you encode 1 to be the number 1, and then for every other number, the encoding starts with 0. It could happen, right? But that's a good guess. That's most likely true, but there could be some pathological exceptions. Okay. Yeah.
Go to a fixed number of binary digits.
That's a very excellent point. Basically, if I fix the length, then any encoding is going to be prefix free, right? Because encodings by definition, we said no two objects will map to the same string. But if the lengths are the same, then the strings must be different. Okay? The problem with prefix freeness comes when you have things of varying lengths, which we have to deal with, right? Because we don't want to put a bounded amount of encoding length. Okay. Yeah. Yeah, they're on the same scribble, but they should be on a different sheet. So each lecture will be on a different sheet. If you go to this icon, got it? Okay, sure. Any other questions? Okay, but on the other hand, so this is not prefix free. Okay. But we also saw another encoding, right? Which was Z2 binary, the new modified Z encoding of integers to binary, where we duplicated each bit and then appended 0, 1 at the end, right? Remember that? Is this prefix free? Is this prefix free? Actually, it is, because we explicitly made it prefix free by adding this 0, 1. So we'll talk about that in a little bit. So for instance, here, when we did so if you go back to last lecture, right? So you can see here that you have the encoding of 1 was 0, 0, 1, 1, 0, 1, right? And so on and so forth. So basically 0, 1 as a pair only occurs at the very end of the encoding, right? So it cannot be a prefix because 0, 1 only occurs once. Okay. So we'll elaborate on that and we'll exploit that really. Okay. Any questions about this? Yeah.
0, 1.
in the second and third characters, so couldn't you technically have read the string incorrectly? For Z to be 1, 0, 0, 1, 1.
So basically, if you look at pairs of bits, right? So if you skip zeros, like, everything is duplicated. You're right that there is a 0, 1, but that's that's taking like a even and odd positions.
So it depends on how we read it.
Yeah, definitely. But, the property doesn't. How we argue about it depends on how we read it, right? So the property that we're saying is that, so let's take the example, right? So Z to B bar of 1 is going to be 0, 0, 1, 1, and 0, 1, right? So because, okay, and right, so these are the usual integer to binary encodings. We just have the sign bit and then the binary encoding. So this is not prefix free clearly because the encoding of 1 is appearing as the prefix of 3. But what happens when we do this duplication? Okay, so you're going to have 0, 0, 1, 1, and then 1, 1, right? Is getting duplicated, and then we have 0, 1. Okay. So for the prefix p property is now preserved because it doesn't match. Okay. Does it make sense? All right. So why are prefix free encodings useful? The reason is the following. So let's ask the question. So why are prefix free encoding special? Can you think of any uses? Maybe not in this context, but in general. Yeah.
We're not going to find a prefix we know it's how we're getting.
Yeah, exactly. Right. So especially when you're communicating, like, when the message ends kind of within the message. You don't have to send a special symbol saying, okay, I finished telling what I had to say. Okay, and that's very important. It's not just for this purpose, but in some cases, even when you're communicating over channels, people use prefix free encodings for this reason. Yeah.
Huffman encoding, prefix free.
Yeah, Huffman encoding is actually prefix free. And if you're doing any, communication course, especially in like information theory and so on, prefix free encodings show up a lot because when you're communicating over a channel, it helps to know when the message ends if you don't have feedback. Okay, but for us, we're looking at a more sort of basic application of it, and it comes from the following sort of simple to state but powerful property, right? And what is that property? So if we have encodings of certain objects, it's not immediately clear to us, or it shouldn't immediately be clear how to go to encodings of pairs of objects. But this becomes much, much easier if you have a prefix free encoding. Okay, so what do I mean? Suppose we have a prefix free encoding E of some collection of objects. It doesn't matter what it is, as binary strings. Okay. Now, just with this, I'm going to be able to define an encoding for lists of this object. Okay, so if I have a prefix to encoding of integers, I can get a prefix, I can get an encoding for all sequences of integers. If I have a prefix to encoding of a single image, I can get an encoding for all sequences of images, and so on and so forth. Okay, so that's the utility of prefix free encoding. Okay, so I'm going to define an encoding which takes any sequence of objects, not just a single object, any sequence of objects, and gives me a binary string. And how do I define it? Any guesses? So let's say, I have some sequence of objects from my universe of objects. Let's call them x1 through xn. Okay. How can I get an encoding for the sequence? Any suggestions? Yeah. Yeah, exactly. Earlier, when we talked about getting encodings for rational numbers, concatenation was bad. But if you have prefix freeness, then concatenation is great. Okay, I'm defining a new encoding for sequences of objects. And now the theorem statement is that this is a valid encoding of arbitrary tuples of objects. Okay. So once we have prefix freeness, we can go from encoding of a single object to any arbitrary length sequence of objects. Does this statement make sense? Okay. So how do I prove this statement, right? So what do we need to show? We need to show that this E bar is actually a valid encoding, meaning that no two sequences of objects will map to the same binary string, right? But we also said that, one way to prove that an encoding is valid is to actually give a decoder, right? So we'll prove this by giving a way to decode, right? So okay, so suppose someone gave us this binary sequence. Okay, we don't know where the splits are happening. We just have this contiguous binary sequence. Yeah, go ahead.
I just had a question. When we have a prefix-free encoding,
Mhm.
if we're going to combine objects together, for example, with our prefix-free encoding, we have 0, 1 to indicate the end of an object.
Mhm.
But do all prefix-free encodings have an indication of where one object ends?
Not necessarily. That's one way to get prefix-free encoding, but there are some encodings which become naturally prefix-free, and they don't have to have like a special 0, 1 at the end.
But would you be able to tell where, like, which sequence of bits corresponds with which object?
You should be able to. That's why prefix freeness is useful, right? Because when you go back, there's nothing which will appear as a prefix, as we will see. Okay. Yeah.
Can you like explain why like without prefix free?
Yeah, that's a good question. So the question was why this idea of concatenating fails if you do not have prefix freeness, right? So let's say you take the N2 binary encoding, which we know is not prefix free, okay? And consider the sequence, which is, let's say I have maybe 2 and 5. Okay, if I concatenate it, what do I get? I get 1, 0, 1, 0, 1. Right? But on the other hand, if I take the sequence, which is, let's see, what is this guy? 2, 7, right? 7 and 1. What do I get? Right? Because 7 is, the encoding of 7 is exactly this. I concatenate it with the encoding of 1, I get this. Okay? So if I just concatenate, then let me put this in quotes. Then it's not giving me a valid encoding, right? If I concatenate the encoding of 2 and 5, I got the sequence 1, 0, 1, 0, 1. If I concatenate the encoding of 7 and 1, I got the same sequence.
Oh, you don't represent like the dot?
No. The dot is, we have only 2 symbols, just the 0 and 1, right? So this dot is just for my notation, really. when you put them together, the dot information is not there. Okay, all you see is just the sequence. That's it. Because that's actually what's there on your hard drive. There's no special symbol anywhere saying this is the end of the file or anything like that. Okay, it's just one continuous 0-1 sequence. Okay, any other questions? All right. So, if I give you this sequence, I mean, now we also saw that the dot information is not present. It's just for my kind of, notation, right? How can I go back and kind of decipher where the breaks are? Any ideas? Yeah.
We have that can be like 0-1 special.
We don't necessarily have it. We just have the prefix freeness property, right? Okay, so if you had that, what you said would work. You kind of skip 2 symbols at a time until you see 0-1, and then, you found a break. But all we have is a prefix freeness here. Any suggestions? Yeah.
Wouldn't it be like you're just reading the first time you see something that matches encoding, you can call that a song.
Exactly, right? So that's exactly the property the prefix freeness allows us, right? So let me write that down. So the decoding algorithm is going to be, I'll just write it in words. Keep reading from left to right until the sequence matches an encoding. Okay, you keep going from left to right. You just keep reading, okay, I have 1, I have 0, I have 1, I have 0, 1, 1 maybe. Keep seeing it until the string that you see is actually a encoding of some object. Okay, until you say valid encoding. And once you see it, you know what it maps to, right? Because it's prefix free. This cannot occur in the prefix of any other encoding, right? It's 1-to-1. So you just chop it off. You found the first object. Okay. Once we find it, chop it off to recover first object and proceed. Okay, so kind of essentially peeling off one object at a time, right? And prefix freeness allows us to do this without any ambiguity. Okay, so in terms of decoding also, it's a pretty simple algorithm. Sorry, everyone, the internet crashed in this room.
Don't worry, the internet crashed all over campus.
All right, let's go with that.
Birthplace of the internet.
Where am I? Hold on, guys. Okay, let's see. So I think we're back now. And is the recording? Okay, the recording is still going on, but I'll. Okay, we're back. So we have a way to decode. So we should be able to encode. Yeah.
Zero, then you have a fraction, the numerator, then it's zero.
Right.
Let's say you combine the two.
Mhm.
What's to like prevent you from saying, okay, the first whole number and the numerator of the fraction is the fraction, and then the third number is the whole number.
So we are getting to decide the decoding algorithm,
Okay,
right? So we have a choice for designing the decoding algorithm. If we use any other thing, it might not work.
okay.
Right? For the mapping to be one-to-one, there should exist some decoding function. That's all we need.
Okay.
Okay. Yeah. Mm. Right. You're right. There might be other cases where this concatenation trick might work, but prefix freeness will ensure that it will work for us. Okay. Yeah. The lecture recordings, they're if you go to the lessons tab, you can add stem and go to lecture 1, you'll see it here. Okay, but if you're looking for this the live link should be it should be on Bruin, or it should be from the course website. You should be able to say a Zoom link on the course website. Okay. Yeah. If you go under the lessons tab, there'll be slides, video, and everything included there. Okay. All right. So let's see. Any other questions? Yeah. So this was a question about what would happen if you concatenated things when you don't have prefix-free property, right? So as an example, I said, let's take the encoding naturals to binary, which is not prefix-free. And we did the encoding, we did this concatenation idea, right? So we take the encoding of 2, concatenate with the encoding of 5. So I get 1 0 1 0 1. The same time, if I encode 7, I get 1 0 1 0. Ooh. I see. Is that 9 or? Yeah, thank you. No. That's 10. Thanks. It's not 7, it's 10. You could have just told me your arithmetic is wrong. Sorry about that. Yeah. Any other questions? Okay, so at least prefix freeness is allowing us this powerful property that, once I have an encoding for one object, I get it for all possible collections or sequence of such objects. Yeah.
Is there a case where non-prefix freeness or whatever, not having prefix freeness is desirable?
I would say not. The only thing is prefix freeness usually comes at some expense, right? For instance, when we did this, as we'll see, you might have to increase your encoding's length. Okay, so in that sense, it might be a bit expensive, but other than that, I can't think of any use. It's always good to have. If you can get it at the same cost, whatever your cost metric is, I think it's desirable. Okay. All right, so we have this amazingly useful object. If we have a prefix-free encoding, then we can compose them however way we want, right? But do they exist? And if they don't exist, then all of this would be pretty useless. So do prefix-free encodings exist? So we can actually not only do they exist, but we can actually compile any encoding into a prefix-free encoding. Okay, so you want to have this ability, right? Because we want an algorithm which takes one encoding and makes it prefix-free, and then we can use it to do this composition. Maybe the composition is not prefix-free, but then again we do this way to convert any encoding to prefix-free, and then we can recurse. Okay. So all of this we want to do automatically, right? We don't want to kind of hand engineer every time. Okay, I want a prefix-free encoding for integers, then I do this. I want a prefix-free encoding for something else, then I do this, right? So what we're actually going to show is that if I have an encoding, there is a way to convert any encoding to be a prefix-free encoding, right? So we define a new encoding, which is from the same collection of objects. And we saw how to do this already, right? The doubling and appending the 0, 1 trick is actually much more general. It doesn't have to be just for integers. It converts any encoding to be a prefix-free encoding. Okay. So what we're going to do is we compute what the true encoding is. Then we replace each 0 with 0, 0. Replace each 1 with 1, 1. Add 0, 1 at the end. Okay. And the claim is that this now gives us a prefix-free encoding. Okay, so kind of completes the circle. Give me any encoding, I can make it prefix-free. Once I have prefix-free encoding, I can concatenate. And then, if you want to, I can again take this concatenator encoding, make it prefix-free, and then repeat. Okay, yeah.
So when we decode that, we just separate each digit as one.
Exactly, yeah. Right, any other questions? Yeah. Yeah. I mean, we could do anything as long as it's different from two things. I think it's fine. The same thing would work. And there are other ways of getting prefix-free encodings from encodings, which are a bit more efficient. And I'll say a little bit, I think, someone asked about it in the last lecture too. But there are slightly better ways as well, many different ways. And some encodings naturally. So the proof of this, is something that we already saw. Basically, if I have X, E of X is something like this, then we've repeated each one. So 0, 1 only, if I keep skipping two bits at a time, 0, 1 only occurs at the very end, right? There is no other place where 0, 1 can occur when you're starting at an even position, because otherwise you're always repeating the same bit. Okay, and that tells you when a string is ending. So that's why it is prefix free. Okay. Okay. Any questions about this? So okay, we are back. So we can represent lists of integers, right? And then we can keep going. We can get prefix free representation of lists of integers. And then we can get representation of lists of lists, right? So for example, I can represent things like right. And if you think about it, these are already looking a lot like, matrices or images or whatever you have. Okay. So this gives us a way to represent anything, any object that we want as binary strings, right? So as a conclusion, from now on in this course, now that we've done it once and convinced ourselves that everything is just binary, we can assume that the inputs to any computational task that we have are going to be binary strings. Okay, yeah. It will automatically do it, right? Because we already said that the list itself is an object. So it should be able to, completely go back and give you it as a list of lists. Okay, make sense? because we declare, so the things of objects. Okay. In fact, this sort of encoding is actually used in Java programming language in the compiler. Any questions? Yeah.
So for this list of lists, so when we're reading it in TP code, we have to read it at 4 bits at a time instead of.
It could be much more complicated, right? It depends on what our, it's all coming from recursion, right? So the only thing we are going to use is that there is some encoder decoder for a list. Okay. And we're going to use that as a black box and then go up one level. Okay. So maybe just hold on to that thought. And we can actually see it here, I think. Wow, okay. Oh, the screen resolution really got short. All right, so if you actually go to LSTM, you can see this code, which kind of implements this idea, right? So suppose I take the representation of natural numbers to strings or binary strings. And this is the representation that we talked about at the beginning. If the number is more than 1, then you define it recursively. You find the encoding of n over 2 and concatenate it with n mod 2, right? And the decoding is also fairly simple because you can just add up things based on the power of 2. So let's run it. If I take the encoding of 2022, it's going to be this binary string. Let's check if it works. Maybe let me make it 2023. Okay. And the idea that we had for prefix-free encodings actually works in more generality, right? So we said you can take any encoder and make it prefix-free, right? And the same thing would also work for a decoder. Like, if I have an encoding decoding pair, I can get a prefix-free encoder and I can get a prefix-free decoder. The decoder is just going to the same thing, which is you skip the last 0, 1 and then kind of make the duplicates into singles, right? Just stare at this code, which is exactly what it's doing. It's duplicating each bit element and then adding 0, 1 at the end. Okay, here you're just duplicating every one and then adding 0, 1. And in the decoder, it's kind of doing the same thing, right? It's removing the last one and then taking every odd position. Okay. So this is a function which takes 2 functions as input. Okay, Python allows you to do that. So we're taking the handles for 2 functions. Here encode and decode are 2 functions, and it is returning to me 3 functions. One, which is a new prefix-free encoder, the prefix-free decoder, and something which checks if an encoding is valid or not. Okay. So if I run it, and I get same thing. Let's say maybe 2021. I get. Okay, so if I do encode 2021, I get this string here. If I ask it to decode this string, I get back the number. So it worked. But now we can use it to get lists, right? We said once I have a prefix-free encoder, it's easy for me to get it for lists, but just concatenating things. Okay. So that's exactly what this is doing. If I want to encode a list now, it takes each object in the list, computes the prefix-free encoding, and just joins them. The decoding is kind of doing something a little bit more subtle, but let's not belabor the code here. But the idea is exactly what we discussed in our decoding proof, right? So you keep parsing until you find a valid encoding. Find a valid encoding, chop it off, and then go on. Okay, that's exactly what this is doing. So if I run this code, now I get 2 more functions, which are now really doing encodings of lists. So this, okay, maybe this is too long. We make it. So the list 131 and 1936 is exactly this binary string. Okay. And to check that, if I ask you to decode this binary string, what do I get? 131 and 1936. Okay. And if you want, you can do the same thing again, but let me not do that here. You can do, maybe 177. Okay. So we did not actually design an encoder for lists from scratch. We just used things, by composing them. Okay. So this idea actually works, as you can see in practice, and it's exactly what we discussed. You duplicate things, add 0, 1 to make it prefix free, and then you concatenate, and that's it. All right. So if you want, you can also go, one more step. You can make this encoding of lists prefix free first, right? And then you get representation of lists of lists. So this is like, let's say, okay. So this is now, this binary string represents this list of lists. And then you can repeat again and again. All right. Okay. So you can, these are simple things to implement. There is a question in chat, which is, how is the list of objects prefix free? What if one list is the prefix of another? So that's a good question. So when we do this concatenation trick, okay, we start from a prefix free encoding, we do the concatenation, we get a valid encoding, but we lose the prefix free property. Okay, so the new encoding we get is not going to be prefix free, but that's not an issue. Why? Any guesses? Like if I want to compose, yeah? Yeah, you run the same trick again. You can make any encoding prefix free. Okay, so that's the main idea behind how people really represent lists of lists and lists of lists and so on. Yeah.
Every single step up you go, does it like blow up all the bits like by 2? So then it's kind of like exponentially, I guess, increasing the amount of bits you're using to encode these.
Yeah, that's definitely true with what we are doing here. But there is a better way where you don't have to blow up exponentially. It only increases additively by a logarithmic amount. Okay, so that's a little bit more involved. So we didn't go into it because we're only interested in demonstrating the principle, right? That's an excellent question. Like, if I do this encoding from arbitrary encoding to prefix free, I'm doubling the length, right? If I do it again, I'm going to double again. So if I take a list of lists of lists of lists, which is 10 times, my encoding is just become 2 to the 10 times bigger. Okay, but it's not necessary. There are better ways to do it where you don't increase it by a factor of 2 every time. Okay. All right, let me switch back to here. And this code is also available for you to play with within EdSTEM. Okay. Any other questions? All right. So summary is the world is binary. Strings. Okay. So we really can represent all objects by binary strings. So from now on, for the rest of this course, even though we're trying to talk about capturing all forms of computation, we're only looking at inputs, which are just going to be 0, 1 strings. And it's a good reason. It's kind of a simplicity. It's for simplicity. It allows us to do this in an abstract way. And we know how to open this black box if we need to. Okay. Any other questions about it? All right. Let's take a 5-minute break. And when we come back, we will talk more about encodings and then jump into computation. Okay. So welcome back. All right. Okay, so we saw how to compose things, and there was a good question about it. So do we need to know what level of the list we are in? Right? And if I keep repeating it, do I need to know the length of the list, or the decode for the decoding to go ahead? You do in some sense, because everything is happening at this level of functions, right? You take an encoder, decoder, and then don't think of it in terms of lists and so on. Really think of it as working abstractly. Give me an encoding, I can give you an encoding of lists of that object. Okay. Now for the next level up, we're going to apply it to lists as objects. But that's again, we're starting from scratch. We just have an encoding. I can make it go for lists of objects. Okay. And so a couple of you asked about efficiency of conversion to prefix-free encodings. Okay, so in what we discussed, the length of the prefix-free encoding of X is going to be 2 times whatever encoding you had plus 2 bits, right? Because we're duplicating each bit and then adding to like the 0, 1 at the very end. Okay. But you can actually get a conversion where the new encoding has length okay, so you're not doubling the length, but if you had a string of n bits, then the new encoding will have length n plus 2 log base 2 of n plus 2. Okay. Kind of, I don't want to belabor this, but you just know that there is a better way. So it's actually a practically implementable scheme. Okay, and in fact, as I said, this is something that gets used in object-oriented programming a lot. Again, much more sophisticated. And if you want to think about it, the idea is to basically use the same trick as there, but not for the entire encoding, but just for the length of the encoding. Okay, so you encode the length of n, which is like log n bits, and then do something with it. Okay. All right. So before going on to talk about how we are going to build our models of computation, operating on binary strings, let me take a small interlude to talk about this power of representations, right? So we said, everything can be represented as binary strings, but it's not really true. Can we represent real numbers as 0, 1 star? Okay. Can I represent things like square root 2, square root 3, square root 5? These are all objects as well. Can we represent them as binary strings? So concretely, you can ask, can we have a 1-to-1 mapping from real numbers to binary strings? Okay. And some of you might, already know this, that there is no such encoding, right? There is no way to represent real numbers as binary strings. And this goes back all the way to Cantor in 1876. there is no one-to-one mapping. Okay, so this statement itself is really, really interesting. And the proof technique that Cantor used is basically what's called diagonalization argument. And we'll revisit it towards the end of the course. Okay. But, I always like to have some historical trivia. So when Cantor actually showed this, what do you think the reaction of the world was? When he showed that real numbers cannot be represented as binary strings. Yeah.
That's just the same, not that surprising, because I feel like those numbers like that would be such a hard.
Sure, maybe now, Okay, let me tell you what the reaction was, right? So there is Kronecker, who was one of the, I'd say one of the big mathematicians back in the day, especially in number theory and so on. He called Cantor corrupter of youth. Okay. Poincaré, whom you know, and kind of, from the Poincaré conjecture and many other things, said should be banished from mathematics once and for all. Okay, and Ludwig Wittgenstein, who is a famous philosopher, said utter nonsense. I guess a bit more, less personal, maybe you could please give him that. So it's laughable. Okay, so it was very surprising that real numbers cannot be represented as binary strings. Okay, yeah.
Wait, you know there was a feedback, like did Kronecker and Poincaré have like
I don't think so. I think it was just very shocking at the time, because back in the day, a real natural numbers, binary string, that was all there was. And what Cantor showed was that real numbers are actually is a bigger infinity than natural numbers, right? Yeah. If you have infinite binary strings, yes. But remember the way we define 0, 1 star. It's always, arbitrary length, but finite binary strings. Okay. And finally, this was back in 1870s, but it took some time for people to accept it. But at some point, people realized the importance and utility of this idea. And in 1925, for instance, Hilbert, another famous mathematician, said, Cantor opened a new paradise for us. Okay, so we will revisit the ideas that Cantor used in his proof later on, but just don't take representations for granted. There are surprises there. Okay, so in summary, as I said, we can view all inputs, be it images, videos, strings, graphs, anything you have as binary strings. Okay. Any questions about this section? All right. So with that, we kind of, we are done with representations. I said at the beginning, computing has two parts. One is representation. You have to talk about what's the data that you're operating on, and then what is the actual computing that you're going to do. right? So we now know what's the data that we're going to operating on. It's just binary strings. And let's dig into how you operate on them. All right. So let's start with another sort of historical anecdote. So we had to now talk about algorithms, right? We said these are operations on data. So does anyone know where this word comes from? Or at least one most likely origin for this word? Okay, I didn't know it until very recently too. So actually, there was a mathematician, Khwarizmi. Okay, who was a 9th century mathematician. And what did he do that made his name get associated with algorithms? Well, he actually gave one of the first algorithms. No, I don't think so. I'm not sure. Okay, perfect. Did he name it after himself? Very modest. Okay, gave a procedure to solve quadratic equations. Okay, so he gave an algorithm to solve quadratic equations. So that gave him, I guess, the credentials to name algorithms after his name, which is great. But hidden in here is kind of an informal definition of what we think of algorithms as. Right? So if I told you, okay, maybe let's not get too rigorous, tell me what should an algorithm be? What would you say? Explain it to your 5-year-old, 6-year-old, 10-year-old. Yeah.
A series of repeatable steps,
Yeah. So
finite series of repeatable.
series of steps to solve some task. Okay, or solve some problem. As we're thinking of, maybe you want to find the largest number in some list, you want to find the sorted order of this list, you want to check if the graph is connected. All of those are kind of certain problems, and our goal is to design an algorithm, meaning come up with a procedure which kind of performs a series of steps to solve this problem, right? And for us, the challenge, of course, is that we want to make this precise. How do you formalize this? Okay, so that is what we are shooting for. And I think this notion of solving the problem, that's relatively easy to describe and formalize, but the notion of series of steps is a bit trickier. Okay, so let's kind of do the easy one first, and then we'll go to the harder one. So the solving the problem part is essentially transform inputs to outputs, right? To desired output. Now you have some graph, I want to make it, I want to transform it into something. You give me an image, which is a color image, maybe I want to make it black and white. You give me a lowercase letter string, I want to make it uppercase letter, okay? So this task for us is what we are going to call specification. And this is an important distinction that I'll keep making, that specification is different from implementation. And for us, a problem is essentially going to be a function which takes some input be it image, graph, sequence of numbers, sequence of strings, a text file, a large text file, anything you have. Everything is just binary strings. So it takes a binary string and then transforms it into something else, which is again another binary string. Okay. So for us, the computational problems are always just of this form. I have some function that's specified by some function, which transforms, binary strings to binary strings. As an abstraction, we can do this because we know everything is binary. Okay. Make sense? Any questions about this? All right. So for example, if I ask you to compute multiplication, then what I'm really asking you to do is, compute the function which takes two natural numbers, again encoded as binary string. We know that the pair of numbers itself is some binary string, and then transforms it to another binary string. We want to compute this function. Okay. If it helps, sometimes, you can think of what's called the truth table. So you have, you can imagine there's this huge, immense sort of infinite table where I have all inputs written in a row and the corresponding output written here. Can I have an input, I have an output, I have an input, I have an output. This is somewhere written up. And this is what gives us our specification. Okay, if you're thinking of like, someone wrote down the software document saying, okay, this is the specification of the task I want to perform. Okay. Any ideas? How can I define steps? Yeah.
Atomic operation.
Yeah, so it better be, something not too complicated, right? I can't say my step is I'm going to factorize numbers. Okay. That's way too vague, right? Because we don't know, we might not know how to do it. So for us, at least to start with, maybe if you know how to do things, then you can use some composition, but really by steps, we want some basic operations. Right, in fact, that's exactly what Al-Khwarizmi did, right? He didn't say my step to solve quadratic equations is to solve quadratic equations. He gave a sequence of like, simple operations like additions, multiplications, a sequence of simple things that you can do to actually solve quadratic equations. Okay. Yeah. He named it that also after himself. Okay. Makes sense. Very powerful. Okay. So with this in mind, let's look at one of the simplest possible operations that you can think of. And this is something you might have seen in other sort of hardware courses. And this will lead us to our first computational model. And this is Boolean circuits. Okay. As I said, we're going to build a sequence of models. This is one of the simpler, but also I think, pragmatically speaking, one of the more important models of computation. So what are Boolean circuits? Essentially, you're just computing with and, or, / not as basic operations. Okay, so we have a sequence of basic operations. These are the only basic operations that we are allowing you. It seems like I'm tying your hands behind your back, but we want to make it very rigorous, right? You compose the steps and you can get anywhere or not, we'll see. Okay, but imagine all you have is like these Lego blocks which will perform and or not, and then you want to put these things together in a sequence or in whatever way you want to do more complicated tasks. Okay, so I'm sure most of you have seen these things before, but let me review it for clarity and notation. Just what are this and or not? So these are kind of also called logical operations. So and for us really is going to be a function which takes 2 bits as input and outputs a single bit, right? So and of a comma b is going to be 1 if a equals b equals 1 and 0 else. Okay, and or is a function which takes 2 bits again and outputs a single bit, is 1 or let's say 0 if both are 0 and 1 otherwise. Okay, and not, of course, is just computes the negation. Okay, so not takes a single bit as input and outputs a single bit. So not of a is 1 if a equals 0, 0 if a equals 1. Okay, so 3 simple functions, each one taking at most 2 bits or 1 bit. Okay, and there's we'll use a notation for it. Again, this comes from logic. But it's useful for us. Denoted or is denoted as a V, and not is kind of denoted as this negation operation or sometimes with a tilde. Okay, all right, and so let's say that these are the only 3 basic these are the only 3 steps that you're allowed. You can maybe compose them however which way you want, but you cannot do anything outside of this. And let's see if we can do something a bit more complicated starting from this. So what if someone came to you and said, okay, I'll give you how many ever and or not pieces that you want, but what I really want to compute is none of those. I want to compute the majority function on 3 bits. Okay, so you have to, I give you 3 bits as input, and you have to tell me what's the majority of them. If there are at least 2 which are 1, then you have to output 1. If there are 2 which are 0, then you have to output 0, right? Equals 1, if you can say a plus b plus c is at least 2, 0 else. Okay, can I compute majority, whatever way, whatever natural notion you might have of compute using just and or not? How can I get from and or not to majority? Yeah. Okay, and how would you combine them? Perfect. Okay, so if you look at this formula here, what it's saying is the majority of 3 bits is 1 only if at least 2 of them are 1. Okay, so let me check if a and b is 1. That means these 2 are 1, or maybe a and c are 1, maybe meaning those 2 are 1, or b and c are 1, meaning those 2 are 1. So this formula would actually compute majority just by using these three operations, right? And if I want to write it as functions, instead of this logical notation, I would get something like R of, so I have and of A comma B, then I have to take R of that with and of A comma C, and then I'm doing and of B comma C. Okay, so as we defined and OR, they only take 2 bits as input. So implicit in here is that if I'm taking OR of 3 bits, then I'm really taking 2 OR operations. Okay. Any questions about this? All right. What happened in here? Okay, it's working. Zoom crashed.
We don't learn how to make software robust in this one.
Not in this class. I think it's a problem with this room or my laptop. I need to figure out what. Okay, so let's do one more example. So, and this example is the XOR operation. So what's the XOR operation? It's basically checks if 2 are the same, then you output 0. It checks for inequality. So if I want to write it as a truth table, then this is the input, this is the output. 0, 0 would be 0, 0, 1 would be 1, 1, 0 would be 1, 1, 1 would be 0. Okay, as long as the 2 bits are unequal, you get 1, and otherwise you get 0. Okay. Can I compute XOR just using AND, OR, and NOT? Yes, how? Yeah.
You have A and B, or not A and not B, and you want all that around.
Okay, so that's, let's see, so not of A let me say and of A comma B, or and of not A comma not B, right? Or of everything and then a not again. Okay, this would work. Or you can also think, you're really checking if the 2 are unequal, right? So one should be 0 and the other should be 1, or one should be 1 and the other should be 0, which kind of tells me maybe I can also do or of and of A comma not B, or comma and of not A comma B. Okay, you can see that basically in majority we could compute it just using OR and. But here we had to use a NOT function, and in fact, if you don't use a NOT function, you cannot compute XOR. You need NOT and OR. Okay. So this is another formula for computing XOR on 2 bits. There are various ways, you can come up with all kinds of ways to compose the simple steps of AND, OR, and NOT to get more complicated things like XOR. Now, I don't want to really torture you, but if I wanted to, I could ask you to do the same for XOR of 3 bits, right? I can define it as zero otherwise. Okay. So if there's exactly 1, 1 or all are 1, you get 1, otherwise you get 0. That's the XOR on 3-base operation. Can you compute XOR on 3 using AND and NOT and so on? Well, you can. I'm not going to write the formula here, but one way you can do it is to use what we computer scientists always do, right? We always solve the problem by redirecting to something else, by misdirection. So XOR on 3 is really XOR on 2 of A comma B, and then with C. Okay. So we use repeatability a lot, right? We know how to do XOR on 2. So let me use that as a building block to do XOR on 3. So I can compute XOR on 2 of A comma B, and then do the same thing for the output of XOR on 2 of A comma B and C. All right. Okay, but this is just kind of, get a sense of what we might be able to do with just and or and not as basic operations. So at the very least, we have some sort of formal definition here. So solve the problem is from now on really going to be equivalent to compute the function. Someone tells me, specifies what the function is, and I want to compute that function. If you think of, if someone asks you to solve the problem of sorting, then it is also computing a function which takes any list and the output is a sorted list. So that's the specification. Okay. How we implement it, how you actually design an algorithm for it is a different story. And basic steps. What are our basic steps? They are going to be AND, OR, / NOT operations to begin with. Okay. And you might wonder why AND or NOT. And there's a good reason why we choose these things, because really we have physical implementations of Boolean operations. Okay, starting from the beginning, the very first computers really were built by using these as basic operations, because we could find physical devices which can do and or not operations. Okay, and in next class I'll show you some demos of it, but basically people had very different technologies for them. Like, there was, the earliest one was something called vacuum tubes, which could implement and not operations. The modern ones are kind of all based on transistors, which again, you build something to implement just one of these basic operations, and then you put them together. Yeah.
And or and not are based off of what's preventing us from just using NAND as our basic.
We could, we can, in fact, we'll get back to that in the next lecture. So that's an important question, like, why choose these basic operations and not something else? Maybe I want to use XOR 2 as my basic operation. What really prevents me from it? Is it a better idea? Maybe, maybe not. We will see. We'll answer like why one set of basic operations might be better, or if at all, than the others. Okay. In fact, NAND is going to be something that's going to play an important role as we go along. Okay. Any other questions? Yeah.
So your definition of X you said it's one is odd numbers, ABC or one. Could you expand on that? Not quite sure that.
So basically, if there's exactly one among ABC, it's 1. Or if all 3 are 1s, it's 1. Okay, so basically it's like XOR 3 of 1 0 0 0 1 0 0 0 1 are 1, and XOR 3 of 1 1 1 is also 1. If you want to write on the truth table. Another way to think about it is basically you're adding up A, B, and C, and if the sum is odd, you output 1. The sum is even, you output 0.
Why is 1 and 1?
It's just the definition of what XOR 3 is. It's basically you're adding mod 2. That's what XOR operation is. Okay. Any other questions? All right. So there's transistors. People have found there's something called DNA computing where you use DNA sequences on cells to implement these operations, and then you can compose them. Okay. You can have chemical reactions. To do it. You can use marbles to do it. There's a really fun demo, especially for kids to play with. It's where you can implement and not operations using marbles, and set up a board. You can configure them in some way, and then you put marbles somewhere, and it does computing for you. Okay, there are life-size demos of it in various museums and so on. And you can also use fluids to do it. There's a whole area called fluidics where you can compute things, build computers just based on pipes. Okay. So you can use any of these things to implement. Okay, so to define Boolean circuits are basically devices, a computer, whatever more complicated things that you can get out of just combining the simple operations. Okay, so what do I mean? To define Boolean circuits, I need another definition, which is something you might have seen in 180 that have directed acyclic graphs, right? Or DAGs. Okay, so what's a directed acyclic graph? It's basically a directed graph that has no cycles. Okay, you take a directed graph, something like this. Okay, this is a directed graph, and this is a DAG because there is no directed cycle in this graph. Meaning I cannot follow this, cannot follow a chain of arrows to get back to the same node again. Okay, so this is an example DAG. On the other hand, if I add a link like this, that will not be a DAG, because then I could follow this chain of links and end up where I started from, which is a cycle. Okay. So if we have that, then we can define Boolean circuits. And to do that, let me also introduce some physical notation for ANDs. If you've taken any architecture class, you might have seen it. An AND gate or AND node can be denoted in this way. I don't know what to call this shape. It's kind of like a rectangle with a smoothed out on one end, where you have two wires kind of denoting the two values that are two inputs to the AND function, and the output is the AND. Should really think of them as like physical wires. So this is the output wire. Okay. R is kind of like an arrow. Okay. And not is this triangle with a dot at the beginning. Okay. So this is the NOT gate. So it takes A and outputs NOT of A. All right. So if I have these, kind of, sort of layout of what these devices are. So now imagine you really have a million Lego pieces where each piece is actually one of these gates. Some device, which takes two wires and outputs the AND. Some device which takes two wires and outputs the OR. Some device which takes a wire and what passes out is a NOT. Okay. We can put these things together to compute other functions. So if we take an example, let's say for XOR, we had a formula which was it's AND, oops, sorry. It was OR of AND of A comma not B and AND of not A comma B. Okay. So I can build a circuit for XOR 2 in this way, where I say, I have the input wire, kind of, this is A, this is B, and I have an AND gate here. Right, and so I should have AND of A comma not B. So I should pass B through a NOT gate. Right, and here I should have NOT of A. Okay, so this is and not, and these outputs are going to an OR gate. Okay, so this is kind of a circuit diagram implementation of the XOR operation using AND, OR, and NOT. So the output here would be the XOR. Okay, if you think of it as a physical device, what it's saying is, if I pass, some electricity through these things corresponding to this bit string 1, then the output will denote exactly what the XOR operation is. All right. So Boolean circuits are essentially what these diagrams would represent. Okay. I give you unlimited number of AND, ORs, and NOTs, and the ability to rewire things. You can connect these wires however which way you want. If this is what you are allowed to do, what functions can you compute? Can I compute everything? Or are there any limitations? Are there more powerful things that I can get by using a different set of gates and so on. Okay. So when we come back in the next lecture, we'll kind of look at this picture, generalize it using the concept of directed acyclic graphs, and then introduce a first model. So if you don't know what DAGs are, kind of revise it a little bit before we come to the next lecture. Okay. See you on Monday.